Hello, I'm a little bit late, so we'll have to start right away. For the contest. It's bad to be late, actually. It's very bad. So, wonderful sticks. Wonderful sticks. We're proud owners of n sticks, 1 to n, distinct. Arrange in a row. Okay. FSI is less than I plus first should be smaller than all sticks before it. If greater than it should be greater than all sticks before it. Okay, it's kinda easy. Oh my god. What is it? I need this one. So, do we have a multi-test? Yeah, we have a multi-test, so we read it. And we read n, then we read a string. Actually, let's just pass the string to the to find ans, and then we need to print it. Simply print it. So what do we do here? This is some crap. So here we do the following. We go, I think, from left to right. Yeah, so let's say vi ans, and we store the minimum and the maximum number that we currently have. Like the semi-interval. So int left is 0, right is 0, and then we go through the string. So if c equals less, then our current symbol should be less than everything before it. So we say ans.pushback l minus 1 and minus minus l. Else ans.pushback r and plus plus r. Okay, this gives us numbers from 0 to from L to R, and we need it from 0 to something. So we need to subtract that. Okay, let's go. So less should be 2, 1, for example. No. Because I need to start from some number. For example, like this and like this. Yeah. 2, 1, 4, 3, 2, 5, 1, 1, 2, 2, 1, 3, 3, 4, 2, 5, 6, 7, 1. Yeah, that's good. Great. Problem B. Actually, it was extremely slow because I was late for the round and because I am unprepared a little bit. Of course, already A and B here. Okay, we have very colorful gloves and we keep them in a drawer. Each one is in one of n colors from 1 to n. Specifically for each n, we have Li left gloves and Ri right gloves. It's late at night, so we can see any of gloves. Minimum number of gloves you need to take out of the drawer to guarantee that we have at least k matching pairs of gloves with different colors. Okay, this is quite a standard problem, but I don't remember how it's solved. So let's first of all read the input, I think. Yeah, so let's read the input. Vi ln, cnl, vi rn, and cin r. And then we need to find uns of L and R and print uns. Right? Okay, so now we have two VIs. And what do we do with that? We want to find the maximum amount of time it will take before we get k matching pairs. Well, basically in each pair. So what do we do actually? So let's say that we have some L1 R1, L2 R2, L3 R3, etc. Ln Rn. So basically what we do is, first of all, let's swap L and R if upper is smaller than the... So I want these inequalities and I can have them. So now what I do actually is I think I need to take all of these, also I take all of these, and I take R or 1 from RK. So I take all left gloves. So after that I take some right gloves and +1 after that. Okay, so I think that makes sense. So let's go. Okay, I want this, I think. For int I from 0 to n plus I. So if li is less than ri, then swap li and ri. Then I add it to the answer. Great. Now when I have done it, I have all the upper part. After that, I sort R, and I want to take the... let's inverse sort. Also, I want a number k, I think, yeah? Where is number k? A number k is given before n. Okay, I go from 0 to k. And say that answer plus equals ri. And after that, plus ans. And return ans. Okay, let's go. So it should be 6. $59 and $97. Why? Okay, it messed up a little bit. Ah, N and then K. Yeah. Six 101 303 10. What about k equals n? Ah, it makes sense. It still makes sense. So I think I can just send it. Why? I need to choose the language. Oh my god. What's wrong with you? Why can't I submit it? Great. Okay, let's copy it again. Problem B. Okay, now it's ready to let me submit it. Problem C. Wonderful city. You are the proud leader in a city in ancient Berlin. Actually, it can fail, so I need to be careful. And square buildings arranged in a grid. Height is hij. City is beautiful if no two adjacent by side buildings have the same height. That's good. In other words, it might satisfy the following. Yeah. No position ij with this and no position that with this. Yeah. N workers at company A and N workers at company B. Each worker can be hired at most once. It costs AI to hire worker I. It costs BJ to hire worker J. And worker I will increase the costs of or the heights of all buildings in row I by 1. Yeah. Find the minimum number of workers of coins needed to make the city beautiful. Okay, so basically, so we have a matrix. Let's instead of this matrix calculate the matrix of what? Let's calculate two matrices. So n minus 1 by n matrix, which is saying, so let's call it R. Rij is equal to ai plus 1 j minus aij. And another matrix which is n by n minus 1, which is column ij equals aij plus 1 minus aij. So we have these two matrices, and when we hire a worker, so we want both these matrices to have no zeros. We want these both matrices to have no zeros. Okay, when we hire a worker who is an A worker, what does they do? They actually never change these differences. They stay the same, but they change these differences. So in this array, what happens? There are a lot of plus ones in some row, but there are minus ones in the next row. Good. So what? So this is actually independent. So we have two independent problems. So work out this matrix, the top matrix, and work out the bottom matrix. Okay, when we have the top matrix. So actually, for each row, what can happen? It can contain zeros, it can contain ones, and it can contain minus ones. If it contains 0, then we need to do something with it. And if it contains ones, we cannot subtract 1, we can only add 1. And the same thing with the minus 1. Good. So it's kind of dynamics. So it's like dynamic programming. It's kind of dynamic programming. So we have the size of the grid. Then we read the H matrix. Vi H of n vi n. Then we read H. Then we have the costs. Okay, and we want to find ans of H, A, B and print it. Nice. So what do we have here? VVI H, VI A, VI B. So for each row, I want to know three things. If there are zeros in this row, ones in this row, or minus ones in this row. That's all I want to know. Right? Right. Okay, so let's create another function. ll find row ones. So vi rows vi a. So in this problem we have like this matrix n minus 1 by n. So what do we do in this part then? First of all, we create a matrix. We create a matrix. I want three matrices. I want actually just one very basic matrix. Three very basic matrices. Has 1, has 0, and have minus 1. So has 1, has 0, and has minus 1. Okay. And let's make it. So const vb vb like row 1 of n, row of n minus 1, row 0 of n minus 1, row minus 1 of n minus 1, and column 1 of n minus 1, column 0 of n minus 1, column minus 1 of n minus 1. Okay, let's go from this. Great. So first of all, if int row difference equals, if ai is +1 is less than n, then let's calculate row difference equals h I plus 1 j minus h I j. So if row difference is equal to 1, then r1 I equals true. If our row difference is 0, then r0 I is true. And finally, if row difference equals -1, then r minus 1 I is true. And the same thing for columns. So we calculate column difference, which is this thing. And if column difference is 1 or 0 or -1, then column 1, column 0, and column -1 is true. And then we want to ll runs equals find row ends of row 1, row 0, row -1, A, and column ends equals same thing for C1, C0, C-1, and B. And if runs is -1 or column ends is -1, return -1, else return the sum. Okay, let's go here. So I want to know 3 numbers. Okay, I want 3 booleans first of all. What can I do with the previous row? With the previous row, P1 is false, P0 is false, P-1 is false. Then I will go through all these elements. In the end, I will say that P1 is H1i, P0 equals H, and also I want 3 answers. Okay, let's also have an infinity. And let's say that we will calculate answer, and if answer is at least infinity, then answer equals -1 and return answer. So ll ans 1, ans 0, and ans -1. And they are all like zeros, if we need it. Okay, so what do we do? In the end, we will do this, of course. But before that, we want to consider several cases. So we'll have ll new ans1 equals inf, new ans0 equals inf, new ans -1 equals also inf. And we will say that a1 is new a1, a0 is new a0, and a-1 equals new a-1. Okay, so what do we do? First of all, we try to not apply a. We try to not apply a. Okay, let's also do this. So if so let's say that this answer says what we added to the row. So if we don't have ones, then we are allowed to add -1. If we don't have zeros, then we allowed to add 0. And if we don't have -1s, then we are allowed to add 1. Good. So first of all, we don't add a row A. Actually, what? Nah, I don't need one of them. I don't need... So when I use this A, this means that I add 1 to all heights, right? Yeah, I add 1 to all heights. If I add 1 to all heights, then the difference between this and the previous one is increased, and the next one is decreased. Yeah, so I do this thing. That means that I can add -1 to the last row, but I can't add 1 to the last row, so only these two apply. Okay, so this is eliminated, this is eliminated. Okay, so first of all, I don't touch A, for example. So if I don't touch A, then I have two cases. I either added -1 to the previous row or not. So what are the cases? So if I don't have 1 in the previous row, then I can not touch anything. So I can say that NA0 is minimum of NA0 and A-1. Also, if I don't have P0, then I can say that NA0 is minimum of NA0 and AM0. No. Yeah. Then let's say that I tried to add something. So I applied this thing. In this case, if I don't have zeros in the previous row, then NA-1 is minimum of NA-1 and A-1 of the previous row. Yeah, so I added -1s, but after that I applied this thing. Now there are zeros in this row, and it's fine. And also, if I don't have -1s in the previous row, then I can apply this. Also I need AI here. Kinda good. I think it can work, but maybe it cannot. I think it might be something off. Yeah. Oh, it should be J here, yeah. Luckily, I found this sneaky bug. Okay, 0 -1 -1, 183. Okay, it didn't notice that here I can work it out. So what was the problem? Let's do like this. Let's go here. I think I want to first of all find this thing. No? It simply said -1. So both Arans and Seans were -1s. I'd like to look into it. So, okay. False, false, true. True, true, true. If we have true, 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 it's basically impossible. But I don't have true, true, true. Why do I have true, true, true? So, no, true to true is fine. True to true basically means that in each pair there is a pair of equal numbers. Yeah, so I think it's fine. So h1 is false, false, true. False, false, true. Yeah. So why did it fail? So I want to look at a0 and a minus 1. Okay, 0, 1. So it said that we can or cannot do this. Mm-hmm. 1, 2. Yeah. So we can both apply an operation to this row or not. Makes sense. Okay, it says that we definitely need to apply an operation to the second row. Why did it say that we definitely don't apply operation to the second row. Okay, again, it makes sense, I think. Ah, I see. So if not P1, then we can make this thing. If not P0, then we can either do this thing or ans and a minus 1 plus a dot back. Yeah. And if not PM1, we can say that ans is minimum of ans and a0 plus a back. Yeah. I think that should work. Oh my god. This problem takes a while, unfortunately. Let's retest that. Let's submit it. I think it can work. However, I am a little bit scared of what can happen. It's fine. Problem D. Infinitely large grid of light bulbs represented by a Cartesian coordinate system. Initially, all light bulbs are turned off except for one light bulb where you buried your proudest treasure. So sometimes we take 4 light bulbs where at xy, xy plus 1, x plus 1, I minus 1, x plus 1, y minus 1, and x plus 1, y. In other words, which switch the state. No constraints on x and y. Then there are n light bulbs turned on at coordinates these ones. Unfortunately, we have already forgotten where you buried your treasure, so now we have to figure out one possible position of the treasure. Input this. Additional constraint, there exists at least one position such that, okay. Hacks are disabled because I think jury cannot check well enough that the test is correct for some reason. I think this should be very easily possible, but they cannot do it. 36 minutes on this problem is crazy. Okay, so what can we say about this thing? So what can we actually do with this thing? First of all, of course, we can see that the number of light bulbs will be odd in the end. We definitely can do it. Another thing that we can do is... Oh, this is actually big. This is actually very big. Oh my god. This is actually very big. Okay. Well, what we can do is let's look at the pairs. So let's take some number Rx from 0 to and 1 and Ry from 0 and 1. Then I think Rx plus 2n and Ry plus 2m. Let's look at all such cells. And you can notice that each such figure is intersecting this set at exactly one point. Right? Okay, that means that we can actually find Rx and Ry for our light bulb. Well, how does it help us? How does it help us? I don't know. Then, what can we do then? Okay, how can we continue that? That process. What about modulo 4? Modulo 4, it's not true. Modulo 4, it's not true. What about maybe x minus y? What do we know about x minus... Actually, x minus y. Yeah, x minus y is also preserved. For example, I mean, x minus y. Yeah, x minus y are 4 different numbers. So we flip all of them, and that means that we also know x minus y modulo 4. That's what we know. Does that help us? Well, let's look at numbers x minus y modulo 4. And let's... So basically what we do is we have a long line in which initially there is only 1, 1. And then we can apply the operation of 1, 1, 1, 1, XOR with this string. Yeah. We make XOR with this string, and that moves it somehow. And then we can XOR with this string and actually put this one here. Yeah, so for example, we had 1 here, and then we have these 3 things. And then we can apply this figure, and we get this, this, and this. So this point resulted in these 3. However, that is not what I want from this. That is not what I want. Do people solve this problem? Yeah, they do, and they actually do it fast. What? 3 minutes on this problem? Okay, maybe later. Actually, I don't have a lot of time. So if it is out there in Chinese archives, I can't spend my time on it. Is it true that I can teleport any point anywhere? So if I can teleport something along this grid, that means that I can simply output any pair of numbers like this. Not like this, like this. And like this. So, so I need to... So I basically want to know if I can teleport it here. So can I move some point to this place? That is my question. Ah. Ah. I got it. So first of all, I can know the vertical position of my point simply because each time I XOR two numbers from each column, so each column will be even except one. And the same for such diagonals. Okay, great. Great problem. And then a lot of pairs of xy. So VPI v n read v VPI ans equals find ans of v and print ans.x and ans.y. Actually, let's read it properly. Okay, first of all, I want to find the proper column. What's wrong with you? Ah, because I already have it here. No, what? Ah, okay. So, I want something like an ordered map, an ordered set. Can I use an ordered set? Actually, they can. Actually, they can. I think let's make it set. Set of ints, columns and diagonals. For order xy from v. So first of all, y is our column. So if call dot what does insert do? It returns an iterate. Okay. If call dot contains y, call. Let's find it. Order call it equals call dot find y. If call it is not call end, call erase call it, else call insert y. Okay, this is about columns. Ah, it should be about axis. It should be about axis. And the same thing about diagonals. Diag it equals what? This is about sums. Okay, in the end, I say that I know y x equals call begin, and I know x plus y equals diag begin, and return x and x plus y minus x. Two, 3 minus 2 minus 2. Two, 3 minus 2 minus 2, 727, 722, 7. Yeah. Okay, can do it here, I think. D, submit. Problem E now. Wonderful teddy bears. Yeah, a proud owner of n teddy bears, which I arrange in a row on a shelf. Each teddy bear is colored either black or pink. Ah, the hacks were turned off. This is nice, actually. That means that probably I could go with unordered maps. So all black teddy bears should be to the left of all the pink teddy bears. Okay. You want to reorder the teddy bears into a beautiful arrangement. We can send instructions to a robot to move them. In the signal instruction, we can choose an index I and reorder the teddy bears at y, I+1 and I+2. Yes. What is the minimum number of instructions needed to reorder the teddy bears? Okay, so if these were 2, then it would be the number of inversions. So this should be something similar to the number of inversions. What actually are the cases? So, okay, first of all, 0, 0, 0, we don't do it. 1, 1, 1, we don't do it. Also, it can be 0, 0, 1, and 0, and 1, and no. It can be 1, 0, 0, and 1, 1, 0. These are the best because I can add 2 to the number of inversions. And finally, there are some cases like 0, 1, 0 and 1, 0, 1. Also, I never touch this and this. And so here I get +1 to the number of inversions, and here I get +2 to the number of inversions. So I want to maximize this number of operations, and therefore minimize this number of operations. Good. So how do I do that? So basically, these kinds of operations are simply when I look at the even array. So array of even indices. Yeah. So what do I mean by that? We have some odd subarray and some even subarray. So first thing that I can do is make this odd subarray like this, and this even subarray like this. And then the question is about this part. So in the end, I have some middle part which looks like 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. And then everything here is ones, and everything here is zeros. So the question is, what do I do with this part? And basically, I think it's something greedy. So I move this one here, and then jump it like this. So this means that I now have 0, 0, 1, 0, 1, 1. So I reduced the number of 1 zeros by 2. Okay. Okay, let's solve this problem. This is kind of easy. It's much easier than 2 previous problems, for me at least. So we read this thing. So we have string s cns vb v of n. So I want black teddy bears is 0 and pink are 1s. So for 0 plus I vi is si equals pink. Then I want to find the answer v, and we print it. Okay, ll find ans const vbv. So there are several answers. First of all, or even ans. Also, I want to find even zeros, odd zeros, even ones, odd ones. Okay, let's go. So if vi, if I is odd, then plus plus odd ones, else plus plus even ones. Else odd zeros, else even zeros. Okay, also I want to look at these numbers. So if I have a zero after several ones, I want to add it. So if I have a zero after several ones, then I want to add it. So here I say that I have plus plus odd uns. And here I have, not plus plus odd uns plus equals even zeros, odd ones. And here I want to say even uns plus equals even zeros, even ones. Okay, so now I have this situation. Now I want to somehow find the number of ones after which there are some zeros. How do I do that? Basically, I want to find the position of the leftmost one and the rightmost zero. Okay, let's find them. Okay, let's say int left. Okay, so first of all, if there are no zeros or no ones, then I return. So let's say ll_uns equals even uns. Let's say ll swap uns equals 0. And if even zeros equals 0 and odd zeros equals 0, or even ones equals 0 and odd ones equals 0. If this is not true, then I will calculate some answer. Otherwise, I say ll_uns equals even uns plus odd uns plus swap uns and return uns. Well, here I want to find the leftmost zero and the rightmost zero. Int left 0, left 1 equals minimum of what? Minimum of all odd zeros, all odd ones and zero even ones. How to find the leftmost odd one? So I have to take odd zeros, multiply by 2, and add 1. To find the even 0, I take even zeros and multiply by 2. So int right 1 equals maximum of right 0. Odd zeros times 2 minus 1, and even zeros times 2 minus 2. Yeah, so I have found the leftmost 0 and the rightmost, leftmost 1 and rightmost 0. Then I want to find number of one zeros, which can be found as the difference this minus this plus 2 over 2. Okay, how many swaps I need for that? So for 1 0 I need one swap. So for 0 it's 0, for 1 it's 1, for 2 when I have like 1 0 1 0 I swap this and then this, so it's 2. For 3 it is 1 2 3 4. For 4 it is 1 2 3 4 plus this situation, which is 2. So for 5 I think it is 9, for 6 it is 10, for 7 it is 16. So I think it's a square in case of an odd number and a triangular number in case of an even number. Oh my god. So if n10 is odd, actually this is crazy that I wrote this here. This is unimaginably bad. So if I have an odd number, then I divide it by, I take swap uns equals, oh my god, n10 plus 1 over 2 multiplied by itself. Great. Else I want a triangular number, which is found as product of these Oh, I love this random formula. N plus 2 times n plus 4 over 8. Okay, great. Let's now check that. I think we will get nice and easy okay here. 0 1 2. Oh my god, no, it did not. BPP, black pink pink. So we have false true true. Well, actually it should be 0. Left 1 is 1, right 0 is 0, and 1 0 should be 0. Ah, what? No, I don't understand that. Ah, it should be 12. Of course, it should be 12. Okay, this formula it was wrong actually. So I need here 3 times. It's not a triangle number. It's like 3 times 4. So it's like n times n plus 2 over 4. It happens. Another one random formula. Okay, 0, 0, 1, 5, 14. Yes. Good. Good, but it's kind of crazy. Okay, problem F. Do I actually have time for problem F? Well, I have time for problem F, but is it problem F that I need to be solving right now? No idea. It might be, it might be not. Okay, problem F and problem G are equal valuable, so I need to read both of them and choose what I like more. A proud live streamer known as Gigi Murin. Today we will play a game with n viewers, number from 1 to n. Game, each player is either a crewmate or an imposter. Among Us? There are m statements from 1 to m. Each statement says that there are no imposters or there is at least one imposter in a segment. Answer Q questions of the following form. Is it possible that statements these are all true? So we have several Boolean variables and we are asking about disjunctions. So it's like set, it's like a linear set. Yeah, so it's basically a linear set. I don't remember if I can solve a linear set. Also, what? A linear set with queries? Basically, how to solve it? Basically, we say that everything with zeros is totally zeros, and the rest of them are filled with ones. So the only way that it can fail now is that some one query is covered by 0 queries. So I have several red segments and some blue segments. And I'm questioned, is it true that there is a blue segment covered with the red segments? Okay, I don't like it. It's probably solvable with some merge segment tree, I don't know. Hmm. No, let's look at problem G. This is an interactive problem. You are the proud teacher of the Millennium Science School. Today a student named Alice challenges you to a guessing game. Alice is thinking of an integer from 1 to n and you must guess it by asking her some queries. To make things harder, she says you must ask all the queries first and she will ignore exactly one query. For each query, you choose an array of k distinct integers, where k is even. Alice will respond with one of the following. L, the number is one of the first k over 2. R, the number is one of the last k over 2. N, the number is not in the array. Question mark. This query is ignored. So why is it interactive if we first ask all the queries? Ah, this is interactive with exactly one response. So we say the queries, we get the answer to these queries, and then we need to print the number, like 5. Why k is even? Ah, k is even so that I can divide the array by 2. Okay. How is it usually solved? I think it can be solved with a trinary system, but then after the trinary system, we need to have some error correction. Yeah, so like we have some trinary system. So basically we write our number as some sequence of trinary digits, an minus 1, etc., a0. And we ask about these digits, so we say like either it is 1 or it is 2 or we don't know. Then about this digit, about this digit, etc., about this digit, and then about the sum. So we can answer this in trinary length plus 1. And we cannot do it in exactly trinary length. Why we cannot? Can we do it in exactly trinary length? So what if we have, for example, exactly 9? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 3 digits. Can we have 3 answers? No, because if there are 2 questions, yeah, if there are two possible answers. So she just ignores one of the questions. Now there are 2 questions. And since we have 10 answers, she chooses 2 equally probable answers and we can choose between them. Okay, very easy problem, I think. And sin n. It's interactive, so I'll have to do some crazy stuff. So we read n. We read n. Basically, let's say that we find ans and we print it, but with envel. Okay, so what do we do here? So we print several queries. Each query is covering all numbers with such digits modulo 3. So what do I do? What do I do? Let's just do it very, like... K should be even. Actually, it's not so easy, because K is even. Oh my god, I don't like it then. I don't like it then. In trinary system. In trinary system, basically, either there are equal numbers with zeros and with ones, or with ones and twos. How to prove that? Suppose that the maximum number is like the minimum untaken number is like a1, a2, a3, etc., at. It's not so easy. So if it is 2, for example, then there are equal numbers with zeros and ones. If here we have 0, then equal numbers with 1 and 2s. But if we have 1, then no. We have several numbers with zeros and several numbers with ones. But not so easy with 2s. So how can I do it more easily without trinary system? Well, first of all, let's say that I have divided all numbers in 3 equal categories, like this, and something else here. Okay, no, actually equal parts, maybe plus minus 1. Then I can take one from here, like this. So 1/3 of these numbers, 1/3 of these numbers, 1/3 of these numbers. Now I have 9 piles. Okay, at each moment I have several piles, each of which has either 0 or 1 numbers. Or either k or k plus 1 numbers. So I have several piles. Okay. Okay, I do something like this, but in the end I have several one piles, and now the problem is that I want to ignore exactly one pile, exactly one query. How do I do that? I want to ignore exactly one query. So I would like to say that I count the number of piles that I lie in. But what if they are not equal? It can happen that they are not equal. Or cannot. I think I can check that. Okay, let's do it somehow. Oh my god, I don't like it. So I have VVI piles of size n. Okay, so int max pile equals n, and while max pile. So is it true that n is at least 2? Yes. So while max pile is at least n, is at least 2, we do something. What do we do? We say that we have VVI new piles. Also, we have like v vector pair vi q queries. New piles. So what? Okay, we say q dot in place back. So we have added a new query. What do we put in this query? So we go through the piles. And we say that the first third of this pile goes to the... We divide it actually just in 3 piles. Yeah, so we say that so if s percent 3 is at most 1, then n0 is s over 3. Else n0 is s plus 1 over 3. Then I say that n1 is n0 and n2 is s minus n0 minus n1. Then I say that I create 3 new piles. So I say piles dot new piles dot in place back for int I from 0 to n0, new piles dot back dot in place back pile I. Then I repeat, but now from 0 to 0 plus 1. And finally from n0 plus n1 to n0 plus 1, n1 plus n2. Yes, and also I want to add it to queries. So I also want to say that queries dot back dot first dot pushback pile I. And here I want to add that query back second pushback pile I. Okay, now I have several piles. Okay, now I want to make a control pile. So let's say VVI control of size 3. Then I go through numbers. And then I go through... Let's just go through all the... Okay, now basically I have... Ah, let's say that the left thing is +1 and the right thing is +2. Okay, so let's say that I just go through the queries. Yeah, so I go through L and say that let's say that let's firstly find residues. Residue of I minus 1 plus equals this +1% 3, and through R it's +2. Okay, now I say VVI control of size 3 for int I from 0 to n if control residue ith percent I minus I dot push back I minus 1. And then I want to test, is it true that I don't know. Okay, so if control 0 dot size equals control 1 dot size, if they're not equal pairwise, if they're all different, then I want to throw runtime error. Okay, else we return 0. So let's run a stress. And here I want to stress. Okay. What's wrong with you? I need to update max pile. So I want to say that max pile is 0 and max pile equals max of max pile and cz of new piles dot back. And same here and same here. What's wrong this time? 4? Why is there are some problems with 4? I need to swap, of course. I want to say that piles.swap new piles. Okay, it failed. It failed immediately. No, what? Pile is of size 5. I think I need to go faster. Okay, it seems that it's fine. It seems that it is fine, right? Okay, let's just go with it. So if these two sizes are equal, then I say that q dot implies back control 0 and control 1, else if and else if. So if here we have 0, 2, then 0, 2. If 1, 2, then 1, 2. Okay, in the end, I need to print all these queries. So what do? I say that I print number of queries. Then I go along. Okay, let's just do it like this. Then I go along all the queries. And I say that I want to find k and all these numbers. Print l dot size plus r dot size, and for I print I, and then along the r. Yeah. Now what? Then I print this character, new line character. Then I want to flash, and I read the answer to all the queries. Okay. So let's say that want correct answers is q.size, basically. Now we go through all the queries and we ask ourselves, so if want I is question mark, then we say minus want. No, not want, but s. Else if si. Also, I want to say vi u of size n. So if si equals L, then basically I want this thing. So for int j from q I dot first plus uj. All right, j minus 1, I think. Else if it is r, then plus this for second. Else it will be harder because for these ones I subtract and for these ones I subtract, but then I add for just all numbers. Okay. Okay, and now I want to find the maximum element here. So I just say return maximum element of u begin, u end, minus u begin plus 1. Okay. Let's say that we don't want on PC files, I think. Let's try it. Okay, it says, what is that? How did it happen? -1? So queries contains -1 for some reason. Maybe piles contains -1 for some reason. No. Also piles. Come again. So queue contains one query. Ah. Something like this. Yeah, probably it makes sense. Okay, if I say, for example, L question, then I am told, what? What's happening? How does it know what to do? Because I have a stress. I see. Okay, let's ignore the stress. Okay, so for example, I print 10. Let's say 2. It says question 1. Okay. 2, I say question n. It says 1 for some reason. Two question n. I want 2. N is impossible. That's why it happened. I see. 2 question r. 2. Okay, let's say 3. 1 2 3 1. So let's say question n. It says 2. Do I want something bigger? Okay, let's try like 9. Okay, for example, I have thought of number 8. So I want to say now no question no. It says 8. For example, again 3. I don't want. Okay, let's submit it. Let's just submit that. Also, did you notice how every problem has something wonderful in it? Please work. I don't I don't want to find the bug in this solution. Let's just pretend that it works and we are fine with each other. Okay, problem F now, probably, because problem H is out of reach. So we have several queries. In each query we know the disjunction of some values. Is it satisfiable? or not. Linear set. I don't know. So let's, like, I don't know, divide and conquer. Let's divide and conquer. So what about this part? What about this suffix? In this suffix, for each disjunction 1, it actually was covered partially with some 0 things. Also, these 0 things covered some of these ones, and so these 0 things covered some of these ones. And also they could partially cover both of them. Okay, so probably it's not a good way. Wow, everything's 25. It's funny. Mm. Maybe I can solve it real fast, although I don't think so. And intervals. Oh, this is some sort of... This is some huge XOR convolution, isn't it? Yeah, it's some sort of some huge XOR convolution. So we have a lot of simple polynomials, binary polynomials, and we want to XOR convolve them a lot. However, naive solution works in the product of these two times, which is not ideal. I can add bits one by one. No, I think it is out of my reach. Okay, imposters. Actually, is my participation already satisfiable? Satisfying? Kinda, but could be better. It really could be better. Okay, we have several segments. And I'm asked a question. Is it true that each blue segment is covered with red segments? And the answer is I don't have any idea. Okay, let's say that I have a segment from L to R, and also let's say that not from L to R. Let's say that I have here L axis, here I have R axis, and also let's say that on the minus first element and on the nth element I have some contradictory thing. It's easy to say that, for example, empty blue segment. In this case, I can say that if R equals n plus 1, it is basically game over. First of all, R is at least L, of course. So I am only interested in this part of the graph. And I can say that this is a contradiction. This is a contradiction, so definitely impossible. Also, this is a contradiction. Is it some sort of two pointers? I want to find... There is kinda some figure of this kind. And I just want to find all these numbers. So I have two types of things. So I have several segments. I have several red segments. And several blue segments. So I have two queries. First of all, I can add a new red segment. And I need to also have some blue segments. I want to check, is it true that now some blue segment is covered with red segments? I can do it only in linear time at best. Secondly, I can remove, also I can add a blue segment. And this is kind of okay. Because if all these R's are in persistent DSU, or some sort of this DSU. In segment tree by minimum. Yeah, in segment tree by minimum. Okay, let's just say that each red segment is just a query in my segment tree that says add 1 to some segment. Then whether B is covered is just a minimum query on this segment tree. So when I add a new blue segment, I basically check a minimum in a segment, on a segment in a segment tree. When I remove a blue segment, it is something like plus plus uns or minus minus uns, where uns is the number of contradictory blue segments. The next thing is adding a red segment. Adding red segment is adding ones to some segment, and then I need to recheck all the queries I had previously, all the blue queries. I don't know. I don't know, it doesn't look good. So I either have plus 1 in a segment tree, or minus 1 in a segment tree. And I need to recheck all the blue queries, which is... I don't know how to do it. Maybe for each blue segment I can do it separately. Yeah, for each blue segment... Okay, yeah, let's just say that for each blue segment, I have some blue segment. I want to find this ladder. First of all, let's say that for each I want to solve this problem independently. So I want to find the maximum segment of queries for which it is fine. Okay, now for each blue segment, first of all, I can find out if it is covered by this thing. No, it's not what I want to do. I think I should go along this bound, along this border, and find everything out. How fast do people solve? Let's agree that I will not solve it because I cannot program anything in 6 minutes. You can see that even problem A was solved in 5 minutes, which is ridiculous. But problem F, okay, if you really want, problem F is solvable in 15 minutes. Or if you don't want it so much, then in 28 minutes. Well, I think Diana tried to solve H, or it really took a long time to solve problem F. It happens. But problem F, okay, so again, I have some segment tree. How many queries? There are a lot of queries, yeah? So can I do it independently? It's kinda a lot of information here. Everyone is spending a lot of time in terms of execution time. Not fast solutions, yeah. Something like n log squared n? Maybe. Maybe there is some greedy approach. Like, I can say that this person is definitely an imposter. But no, I cannot. At any time, it might happen that any subset of imposters becomes non-imposters. Well, so this is a hard problem, yeah. It's good that I at least solved G because I could have gotten stuck on problem G. I could have gotten stuck on both problems. Well, it seems that it should be solvable with some more algorithm, so I really should be able to combine two segments of statements. The only problem is I don't know how to combine these two statements. So we have a lot of red and blue segments. So we have two segments trees. We have a lot of segments, and I want to find the maximum of all minimums on these segments. And the set of segments combines, and the two segment trees are added. I really wonder how it's solved. How it can be solved. I can attach a resource. Oh, it's funny. It's funny that I can attach a resource during the contest. So I can write an editorial for you and attach it here before the end of the contest. It's hilarious. I simply can publish an editorial for you guys if I wanted. Dude. Okay, is there some sort of editorial immediately for me? No. No, there isn't. Hmm. Okay, let's go really fast along all the problems and I will briefly explain them. Problem A. Problem A. So we have a string of such letters, and each letter says, for example, this letter says that this element should be greater than all before it. So 5 should be greater than everything before it. This element says that this should be less than everything before it. It says that this element should be less than everything before it. So you're given this string and you need to construct a permutation of numbers from 1 to n with this condition. Okay, this is a constructive problem. Moreover, I can say that the answer is unique. Although it is a constructive problem, the answer is unique. Why is it unique? So for example, n equals some number. Okay, 5 is actually fine. Let's assume that we have 5. N equals 5. If the last symbol is less than, this means that it should definitely be 1. If it is not 1, then 1 is somewhere else, and it cannot be greater than the last element. So the last element should be 1 if the last symbol is less than. In the same way, if the last symbol of the string is greater than, then you have to have here a 5. Because if it is not 5, then 5 is somewhere else, and it is greater than your last element. Therefore, the last element is either 1 or 5. Then the rest of the elements are some permutation either of elements from 1 to n minus 1 or of elements from 2 to n. Okay, then basically you can prove by induction the uniqueness of such string. So base is for n equals 1, where you can only have one answer 1. And the induction step is, as I said, you find the last element. It can be either 1 or n. And then the rest of the elements satisfy this string. For this string, there is only one permutation. So there is only one permutation of numbers 2, 3, 4, 5, which are aligned with this string. So the induction step is finished. However, to solve this problem and to find the string, actually it is more convenient to go not from the last symbol to the first symbol, but from the first symbol to the last symbol. So I will say that I will find a permutation, but not of elements from 1 to n. Not for elements from 1 to n, but for some elements from minus L to n minus 1 minus L. So I will find some permutation of some contiguous segment of integers, but not necessarily this one. Okay? Okay, initially I don't have any symbols, so I have an empty string, and it corresponds to any number. For example, 60. 60 is a good answer because it is definitely a contiguous segment, and it satisfies all these symbols. So there are no symbols here. Okay, now assume that we have some permutation of some segment of integers, which satisfies, for example, this string. I don't know. Let's look at the next character. Next character, for example, is greater. This means that next number should be greater than everything here. For example, numbers here, minimum is x, for example, and the maximum is y. Then I can simply put here y plus 1. And now I have, again, a contiguous segment which satisfies these relations. Similarly, if I have here a less than sign, then I put here x minus 1. After that, my segment is stretched either with this direction or this direction. In any case, I have a new segment, I have a new array, and after processing all these characters, I have finally an answer. In the end, I have an answer not necessarily from 1 to n, and to fix that, I need to subtract minimum and then add 1 to all elements. For example, if I had in the end minus 3, minus 5, minus 4, then the minimum is minus 5, and I need to subtract minus 6 from all elements so that I get 3, 1, 2. That's it. Quite an easy problem. Let's switch to problem B. Problem B, wonderful gloves. In this problem, you have several left gloves of the first color and several right gloves of the first color. Also you have some two numbers of the gloves of the second color, the third color, etc. You want to you want to get k pairs of gloves of different colors. That's it. But each time you take one glove from the drawer, you don't know its side and its color until it's taken out of the drawer. And you want to find the minimum number of gloves that you have to take from the drawer to guarantee that you will get k pairs of different color. How to do that? Well, I claim the following. Let's first of all note that if I take any color, for example, the first color, and call these gloves right ones and these ones left ones, it doesn't change anything. Because what I really need is I need two gloves of different size from this color. It doesn't matter if I first take the left one and then the right one, or vice versa. I need to get two gloves of different size. That means that I can call either side left and the other one right. And I can do it independently for each color. Because if I have, for example, left glove from this color and right glove from this color, it does not help me at all. I need two different sided gloves of the same color, not of the two different ones. So first of all, let's just swap or not swap gloves in each color so that we have these conditions. This is just for simplicity of the solution. So now for each color, I have more left gloves or equal than there are right gloves of this color. The second thing is let's sort all these colors by the right thing. So let's say that we have this condition. Why can I do that? Again, for the sake of simplicity and without loss of generality. Now I claim that you will have to... So I say that in the worst case, you take all left gloves and all the right gloves up to k minus first color. And then you take exactly one glove of the kth color of the right side. So the answer is L1 plus L2 plus etc. plus Ln plus R1 plus R2 plus etc. plus R k minus 1 plus 1. So this is the answer. After you have sorted each glove first left then right, and after you have sorted in decreasing order all the colors by the number of right gloves of this color. Okay? This is the answer. I claim that. First of all, let's prove that it might happen that you take so much time to find the k-pairs. Indeed, it might happen that firstly you get only these gloves, then only these gloves, and only these gloves, etc. Only in these gloves, and then all these gloves, including k minus first color. Note that up to this moment you still don't have k-pairs of different colors. You just don't have any pairs of different colors except these colors. And then you get any one glove from this set, which gives you the answer provided here. So I claim that the real answer to this problem is at least answer. It definitely might happen that you need this number of gloves. Now I want to prove that real answer is at most answer. That said, it cannot take you more than this amount of time to get everything nice. Why is that? Well, how to prove that? How to prove that if you take at least this number of gloves, then you definitely get k different pairs. Assume that you didn't get k different pairs. What does it mean? It means that I don't know how to... Okay, let me make it bigger. So assume that you have L1, etc. Ln, R1, etc. Rn. And you have taken Ann's gloves, and you still have at most k-1 pairs. Okay? Let's take as many gloves as possible. So for example, if we took some number of pairs and we still can get at least one more glove without getting k pairs, then let's take it. So let's take the maximum counterexample to this problem. So let's look at some pair. What can happen in this pair? Either we have only L1s, or we have only, and if we have only L1s, then we can take as well all L1s, because it will not change the number of different pairs we have. Or we can have all R1s, or we have both all L1s and all R1s. So if we have all else, let's call it type 1. If we have all R's, let's call it type 2. And if we have all else and all R's, let's call it type 3. Okay? Then the answer, then what we have, gloves, is equal to sum Li, where I is from type 1, plus sum of Ri, where I is of type 2, and plus sum of Li plus Ri, where I is of type 3. Okay? And we still don't have any pair. Note that this means, first of all, let's again make this sorting procedure as I said here. In this case, I want to claim that type 2 is empty. Why type 2 is empty? If you have all Ris, but you have none Lis, instead you can take all Lis, and it will make your process longer or equal, because Li is at least a Ri. That means that you can actually claim that second set is empty, and everything from it can be just put in the first set. So we have eliminated this thing. So now this is the answer, and we also know that the third set by size is at most k-1, because if it is at least k, then we have k pairs. Okay, now I can rewrite it as sum of I, all i's, li, plus sum of Ri's, where I is in the third set. And that means that my answer is sum of all li's plus sum of some k-1 Ri's. Actually, I can have here equals. I can have here equals, because if it is less than k-1, then I can have more pairs. I can take more gloves, still not having k pairs of different colors. So I need to take some k-1 R's. And definitely if I want to take some k-1 R's and I want to maximize the process, then I want to take the biggest k-1 R's. So that's why I sorted R's in decreasing order and took the first several R's. So that's the answer. So the process is easy. So first of all, you take maximum from each pair to the answer, and the minimum from each pair put into a vector. Then you sort this vector, it will be the vector of R's, and you take k-1 top elements from it, add it to the answer, and also add 1. And don't forget to make long longs in your solution, because the sum of a lot of billions is not going to fit into an int. Okay, problem C. Wonderful city. Okay, this is a little bit boring problem. So you have a matrix. of integers. You can add 1 to any row of this matrix, actually to any subset of the rows of this matrix. But this is not free of charge. So you can add 1 to the first row for A1 coins, to the second row for A2 coins, to the third row for A3 coins, etc. You can take any subset of the rows, but you cannot add to the same row several times. Similarly, you can do it for columns, for costs B1, B2, etc., Bn. You are asked, what is the minimum cost to make the city beautiful? The city is beautiful if there are no such domino with same numbers, and there is no such domino with same numbers. So each number is different from all its neighbors. Okay, to solve this problem, let's take a difference matrix. Difference matrix n-1 by n is a matrix where each element is equal to the difference of this element and the upper element. So the difference of each of all dominoes is put in this array, let's call it R. Then what we want to achieve is that any element of R is not 0. That's what we want. Okay, let's look what happens when we apply an operation. When we apply an operation to some row, basically what we do is we add 1 to ith row, but we subtract 1 from the next row. Also, it might happen that we only subtract 1 from the first row, for example, or we can only add 1 to the last row. Also note that the second operation does not do anything with R. So B's do not change R. Only A's change some rows of R. Similarly, there is a matrix n by n-1 called C. And in C we can make the same thing but with columns. And subtract 1 from the subsequent column. Okay. And we want to have no zeros in either of these matrices. When you have done it, you can actually solve the problem independently. You can just solve the problem with matrix R and array A and find some answer R and find the answer for C and B, which is called answer C. And you simply add these two answers. And note that if the answer is impossible in any of these two cases, then you also need to print impossible. Okay, so let's fix on only R and A. What do we do? With C and B, it will be absolutely analogous. Actually, we don't want any zeros, so for each row, we are only interested in 3 facts. Is there at least 1 0? Is there at least 1 1? And is there at least 1 -1? Why is that? Because in the end, after we have applied all operations, in the end, each row is either stayed the same without any changes, or 1 is added to it, or -1 is added to it. Nothing else could happen with any row. So with each row, either it is stayed same, or added 1, or added -1. And because of that, only the presence of zeros, ones, and -1s in the initial array is what matters. So actually, instead of this matrix, I could have simply three facts. I just want 3 binary arrays. So either there are ones either there are zeros in each row of R, or there are minus ones in each row. This is what I want to know. 3 Boolean arrays. Okay, then this is some sort of dynamic programming. So let's look at some subsegment of operations. So we have done something to some subsegment of some prefix of the rows. Then what do we know? The last row can still be touched by the next operation. Yeah, because each row is actually affected by 2 operations. By operation with the row before it and operation with the row after it. This operation subtracts 1 from this row, and this operation adds 1 to it. And if both are applied, then the row is unchanged. So what is this dynamic programming? I want 2 numbers. What is the... So let's call it A0 first of all. A0 is minimum cost that I can spend to make all these rows good without zeros. And to this row, I did not add anything. So I did not apply this operation that affected these 2 rows. This is A0. And the second thing I want to store is A minus 1. What is the minimum cost to make all these rows good without zeros? And this row, from this row, I subtracted 1 by this operation. It will be plus infinity if it is impossible. Okay, I have 2 numbers. I want to find A0 prime and A minus 1 prime for the next row. It is easy. I consider 4 cases. 4 cases of this and this lower index, and times 2 cases of whether I apply this operation or not. For example, if I apply both these operations, then it counts here, and I say that it is AI, where I is the cost of this operation, is the number of this operation, plus A minus 1. And this can only be applied if it's fine for me to have here added 0. So I want not M0I, where these 3 arrays are called M. And the same thing, for example, if I applied this operation, but I did not apply this operation, that means, for example, that I again update A minus 1 prime with number AI plus A0, but I can only do it if I'm fine with adding 1 to this row. And this can only happen if not M minus 1 of I. So this is a really easy consideration of cases, and in the end, you find the minimum cost with this dynamic programming. Okay. Okay, next problem D. Wonderful light bulbs. Wonderful light bulbs. Kinda easy problem, but at the same time, it's hard if you are stuck. So we have some plane of booleans. So we have an infinite integer plane of booleans. Initially, only one boolean is set to 1, and all the rest booleans are equal to 0. So all zeros here. you are allowed to take this shape and switch everything in it. So each 0 becomes 1s, and each 1 becomes 0. So something like this. So these kinds of operations are applied to this figure, and in the end we get some Boolean plane again. It is done finite number of times, so some Booleans are now zeros, some ones, some zeros, etc. So we have some Boolean plane that happened to be in the end. The question is to find what the initial x and y were such that. So what was the initial plane actually? What were such x and y that this was the initial state? No, actually, x and y were like this. So you know the final situation. Find the initial situation if you know that exactly one Boolean was set to true there. Okay, first of all, let's solve this problem when your mask of inverting is not this tetramino, but this shape, so just a square. Actually, in this case, the problem is very easy. Let's look at the XOR of, for example, some row. So let's have row y, and look at the XOR of all values. Actually, it's an infinite XOR, so we cannot so easily find this XOR. However, we know that only finite number of Booleans here are ones, so the XOR is simply the parity of this finite number of ones. So what happens with the XOR of any row? If I make some operation, it either does not change if it does not intersect with this row, or if this square intersects this row, actually the XOR still does not change, because 1, 1 turns to 0, 0, and the parity is preserved, and 0, 1 is exchanged with 1, 0. Also parity is preserved. So you cannot change any XOR of any row. Okay? Initially, there is exactly one row with odd XOR, and there is exactly one column with odd XOR. Therefore, initially you can find this x and y simply by checking all rows and all columns and finding the only ones with an odd XOR. Well, this is true after any number of operations with squares, because after each operation, the parities of any rows and any columns are still the same. So the solution is as follows. You have your final board, you go through all rows and find the single row with odd XOR. You do the same with columns, and at the intersection of these two row and column, you get your answer. That's it. Good. Now, what is with this shape? Actually, it's almost the same, but instead of horizontal and vertical rows, now we cannot take them. Yes, any vertical row preserves the parity. However, not every horizontal row preserves parity. This row, for example, can change the parity. What does preserve the parity is diagonal rows of this kind. So in each of such diagonal rows, so with x plus y equals const, you can notice that the parity is preserved. So what you do here is you find the only vertical row, the only column with odd XOR, and the only diagonal x plus y equals const with odd parity. When you do that, at the intersection of them, there is exactly one cell. So you know the x of your incredible cell, and you know x plus y of your incredible cell. And then you can subtract them to find y. And x and y is your answer. To find the only row or only diagonal with this condition, for example, you can use unordered map. So you just say plus plus unordered map of x and plus plus unordered map of x plus y for each x and for each cell that is turned on in the final board. And then you go through this U, unordered map U, and find the only odd element in this unordered map. Okay, that's it for problem D. Now problem E. Problem E, and I will also prepare problem G, because I solved problem G. Wonderful teddy bears. Okay, wonderful teddy bears. I think I did not actually prove it very strictly, but what this were my this was my reasoning. So we want to sort an array which is binary, a binary array. We want to sort it. We can take any subsegment of length 3 and sort it separately of everything else. So the rest does not change, but these 3 elements become sorted. We want to find the minimum number of operations to sort the whole array. First of all, if the subsegment were of length 2, subsegments were of length 2, this would have been a standard problem of finding the number of inversions of the array. Moreover, it is very easy in the case of binary array, because you simply count the number of zeros. Initially it is the number of ones. You count the number of ones, which is initially 0. You go through all the elements, and each time you see a 1, you say plus plus ones. And each time you see a 0, you say that answer plus equals ones. Because in order to sort this array, you at least need to put this 0 to the left of all the ones that are to the left of it. And this can be calculated with this simple cycle. So go through all elements, and if you see 1, then plus plus ones, and if you see 0, then answer plus equals ones. Okay. So you want to maximize. So you just want to, you will have and you will want to spend the number of inversions in your array. However, here with each sort of 3 elements, something else can happen with your number of inversions. So let's see, if you have 0, 0, 0, or 1, 1, 1, or 0, 0, 1, or 0, 1, 1, then you have no need to sort them. They are already sorted. So number of inversions will be not increased. Also, there are 2 types of arrays, this and this, which will become sorted, and the number of inversions will decrease by 1. So here you simply swap these 2 elements, and here you simply swap these 2 elements, and the swap of 2 subsequent elements changes the number of inversions by 1 in this case. And finally we have 0, 1, 0, 0 and 1, 1, 0, where you have this swap, and this swap actually changes the number of inversions by 2. So if you want to minimize the number of inversions, to minimize the number of operations, you want to make the number of inversions equal to 0 as fast as possible. So you never apply these operations, and you want to maximize the number of these operations. You want to maximize them, and the number of these operations subsequently should be minimized. But it will be automatically minimized if you maximize the number of these operations. Okay, I didn't really prove that, but what I noticed is that in these two cases, you actually don't touch the middle element and the edge elements are swapped. That means that you preserve the parity of the index of each element. What I mean by that is, for example, let's assume that this number I is even and number I plus 2 is even. Even and even. Then if we consider an even subarray and an odd subarray, then in the odd subarray nothing changed. Odd subarray is the same as it was before the operation. And in the even subarray, you swapped 1 and 0. Okay? Or vice versa, you swapped 1 and 0 in an odd subarray and you never changed the even subarray. What I wanted to do after that is, first I wanted to sort even and odd subarrays independently. That way I can get here 0, 0, 0, 0, 1, 1, 1, 1, 1, and in the odd subarray also several zeros and several ones. I can do it independently, and I only apply these types of operations, so this is kind of good. So I greedily make only these good operations that fix 2 inversions. After that, I cannot do any more of that because, well, because I cannot. Because any such operation would make either odd or even subarray more sorted, but they are already as sorted as possible. I cannot make it even more sorted. Therefore, I am forced to make this type of operation. Yeah. I'm forced to make this type of operation. So I do. For example, I move this one to this array. And then I again apply these types of operation to move this one to the rightmost position. And I continue that until I have the number of ones and zeros in these two arrays balanced, so that the whole array is sorted. So actually, let's write the answer. So the answer is the number of inversions over 2, I would like to say, if each time I made an efficient operation. However, I have to sometimes make an inefficient operation, so let's add inefficient operations here. Now the formula is correct. What is the minimum number of inefficient operations? Well, note that each efficient operation does not change the what's called the content of these two arrays. So the number of ones in the even array does not change from efficient operations, because efficient operations simply swap something in the even array or swap something in the odd array. They cannot interchange between these two arrays. And each inefficient operation swaps exactly 1, 1 and 1, 0 between two arrays. Note that I know the minimum number of swaps that I need to make, simply because in the end I know that my array is sorted. So I know the final sorted array, so I know exactly how many zeros and ones should be in the end in each of these arrays. And if these numbers differ from what we have initially, for example, here I have 7 ones, and here I have 5 ones. This means that I will have to transfer 2 ones from here to here. So I find the total number of inversions. I find the difference from how many ones there are in the odd part and how many ones there should be. And this difference is called the number of inefficient operations. And then I sum them and divide by 2. Well, to prove that this is an actual answer, I need to prove that there is an algorithm that makes exactly this number of inefficient operations. And this is indeed it. The algorithm that I told you before is making exactly this many inefficient operations, because each time it makes an inefficient operation is in the end when we already have both of these arrays sorted, and it indeed transfers exactly 1, 1 from an array where it shouldn't be to the array where it should be. Therefore, I never do any more inefficient operations that I needed. And indeed, no such operations where nothing is sorted. That's basically it for this problem. Well, I did it a little bit another way because I didn't realize, for example, now I proved it to you, but during the contest I didn't have a proof. I had a feeling that it is correct. Now you have a proof, and you can implement the solution now in this way, not in the way I did it. And finally, problem G, because I will not explain problem F because I don't know how to solve it. Actually, here I also don't have a proof. So the problem is as follows. You have a friend. You have a friend. The friend guessed a number from 1 to n. You can several times ask your friend the following. You can give them 2 sets of equal size and ask, is it true that your number is in L or in R? And note that L should be disjunct. L and R should not intersect. Okay, friend can ask. Also, the size of L is equal to the size of R. The friend can answer either that the size can answer L, so that their number X is in L. X can be in R. Also, they can say N, which means that X is not in either of these sets. And also the friend can say question. That means I'll not answer. However, this type of answer can be given at most once. You cannot give it twice or more. Your friend cannot. You need to provide. Also, these queries are given offline. So you firstly give all your queries and only then friend answers all of them. You cannot give them one by one and await for the friend's reply on each of them. You need to give them all in one batch. So this is a usual, this is a standard application of so-called correction codes. So correction codes is a topic of sending some data over a corrupted channel, a channel that can sometimes make errors. For example, it can skip some bits that you sent, or it can change some bits that you sent via it. And if it could do it every time, then of course you are doomed. Each time you get a symbol, you get 0 bits of information because you have no information of whether this bit is correct or it is not correct. However, if there are some, for example, probabilistic restrictions or cardinality restrictions, then you can sometimes solve this problem. In this case, we have the following thing. We get to know that each answer, we get to know that among all our answers, only one will be skipped. So it never swaps any two answers. It never gives a wrong answer. So it's not true that you will give all answers, but you don't know which of them is wrong, for example. One of them is wrong and you don't know which of them. You know which of them is not answered. In this case, you need something which is called control sum. What is a control sum? Suppose you have n chunks of data. You send all of these chunks to your friend. However, if there is a problem with one of the chunks, you cannot detect it. For example, there is a cosmic ray which flew into your array and changed 0 to 1. You will not notice that, and friend will not notice that, and now you have corrupted data. What you can do is you can send also a control sum of this data. For example, you can take the same sized array, which is equal to XOR of all these arrays. This way, friend can get all these n+1 chunks, and they can check, is it true that the XOR of all this data is 0? Or in other words, is it true that the XOR of these arrays is equal to this array? If it is equal, then if there were errors, there were at least in 2 arrays. Yeah, it had to corrupt something, and it had to corrupt something else, this or this, in order to preserve the XOR sum. But if there is an inconsistency, then friend knows that something is broken, and they can send back to you an information, please resend the data, my control sum is not working. Well, it is exactly same here, but instead of detection of the error, we can also fix the error, simply because we do not get the error as here. We do not have a flipped bit. We have simply a question which says we don't know what is written here. But if you have a control sum, you can restore this question mark by knowing the sum and all this data. Okay, now let's go to the problem. So actually, each time you can ask from your friend some ternary data. The friend gives you, if it is not a question mark, you get a legit R, L, or a legit R, or a legit N. So you can get digit 0, 1, or 2 easily. So intuitively, first N queries, you get some numbers 0, 1, and 2. let's assume that these are enough to restore the number. And of course, they should be enough to restore a number, or else when your friend sends something, 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 and then a question mark, this data is not enough to restore the number. So these n ternary digits should be enough to restore a number. However, there can be a question mark among this data. Because of that, let's also send n plus first digit, which is ternary sum of all these digits, modulo 3, also 0, 1, and 2. Then, if your friend corrupts this digit, you can restore your answer. If your friend corrupts this digit, for example, then they did not corrupt this digit, so you know the sum of all numbers, and you know all numbers except 1. Then you can restore this single number. Okay, how to do it? Firstly, let me explain you the solution where this is not needed, where this equality is not needed. If it is not needed, you can simply write your number in ternary system. For example, n equals 7, you write it as 2, 1. Okay, for example, not n, but x equals 7 to 1. Well, you should be... first of all, I replace all numbers from 1 to n to numbers from 0 to n minus 1 because it is easier for me. Now, yes, you simply encode it with ternary system with possibly leading digits. And now each question is it true that this number digit here is 0 or 1? Is this digit 0 or 1? Is this digit 0 or 1, etc. After you do that, in the end, your friend simply gives you all ternary digits of this number, and you can restore this number by turning it back to decimal system. That's it. Actually, this is the solution. Write your number in ternary, find the set of all numbers with these ternary digits 0 or 1, and print them. The problem with this approach is that actually L will not be equal to R. In this solution, it is false. For example, if n equals 7, let's see, we have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0. Yes, that's it. Okay, in this particular case, it's fine. Let's take, for example, 5. N equals 5. Okay, here, the second digit is okay, because there are two numbers with zeros. So let's say that L0 is 2, because L0 is 0 and 3. L1 is also 2, because it is 1 and 4. And L2 is 1 by size, because L2 is 2. Right? So this is L2. No. It should be R0 and N0. Sorry. R0, N0. R0, N0. So for this digit, everything is fine. There are so many zeros in this column as there are ones. However, if you take the first digit, it's not the same. L1 is 3, R1 is 2, and N1 is 0. Now when I think about it, I suppose... No, I don't know. I don't know how to solve it with ternary system as it is, because there is always a chance that it will be imbalanced, which is not good. Yeah, I think it's not good. Well, if n is even, I think you can get numbers from 0, 0, 0 to n over 2 minus 1, and from 2 to 2 to 3 to the n minus n over 2. Something like this. I think it's 3 to the k. I think it's possible. Yeah, but if n is odd, then it's somewhat harder, and I don't know. I don't know, yeah. Maybe you take all these numbers and the last number will be 3 to the n minus 1 over 2. Yeah, something like this. Yeah, I think it can work. So you have half the numbers the minimum ones, half the numbers the maximum ones, and if needed, one number in the middle, which consists of ones. I think it should work. What I did instead was I took, let's call a pile the set of numbers which are now indistinguishable. In the beginning, we have all numbers in a single pile because we didn't ask any questions. Then each time I say the following. I have one pile, for example. I divide it into 3 almost equal parts, and you can divide any number into 3 parts such that n0 equals n1 and n2 minus n0 is at most 1. So 2 equal parts and 1 almost equal to them. And after that, we say that this will be L, this will be R. Also, this makes this pile into 3 piles. So now we have 3 piles. In the middle of the process, we will have several piles. And what we do then is we do it independently for each pile. So each pile is divided into 3 parts. 2 of them are called L and R. And this gets us to 3 piles. Also LR and N. Also 3 piles. Etc. etc. And in the end, all L's are concatenated. All R's are concatenated. And this is our new query. We do it until we have all piles of exactly one element. That means that we can distinguish all elements. However, this is what we can do without error correction. Then we add an error correction and we calculate how many. So for each number x, there are some L answers L and R answers R. Then I calculate L plus 2R modulo 3. And this way I get some n0 numbers with this number equal to 0, and 1 equals the number of elements for which this is 1, and n2 elements for which this is 2. I add as an error correction these 3 sets. However, in order for this to work, I need one of them to call L and one of them to call R. And I can only do it if L and R are of equal size. Well, actually, for some reason, it is always the case. It always worked that some 2 of these 3 sets are equal in size. I wrote a stress in order to do that. So I just ran it for a lot of numbers up to 1000. And here in findAnse function, here I checked that one of these 3 ifs worked. And for some reason, I don't know for which reason, it worked. You can prove it. I can leave it as an exercise for you that always one or two of these 3 numbers would be equal. After that, when we've done it, we simply add it as our control sum. And in the end, we can simply do the same thing as before. So find the question mark. If it is control sum, then ignore it. If it is not a control sum, then find what should be here via the control sum. You get some ternary string of digits. Then intersect all sets Li's or Ri's or Ni's corresponding to these digits. And then when you have intersected them, you have only one number which satisfies all questions. And you print it. So if it won't work, I would have had to come up with something else, but it wasn't the case. Everything worked fine, and the problem was accepted. This leaves us on some conventional place. Which place? I have 67th place. I think it's fine. I think it's good, yes. For problem F and problem H, I don't know what to say. I didn't solve them. I tried solving problem F, but I don't know what to do with it. So if you want, you can try it yourself. Oh, thank you for watching, I think.